Hello everyone, my name is Vivek Miglani from Facebook AI. This talk illustrates in detail how padding impacts CNNs and can lead to blind spots. To understand this, let's examine how padding is consumed in the presence of strides. In this example, because the width is an even number, when the kernel reaches the right side of the image as shown, it cannot shift by the stride of 2 again, so the padding on the right side is ignored. This means that the filter learns to encounter 0 edges on the left side, but not the right side. A similar effect would occur with inputs of even height, where the filter learns to encounter 0 edges on the top edge, but not the bottom edge. This affects ResNet and MobileNet models because they perform downsampling by means of strided convolution. This can actually skew the learned filters, especially when it happens repeatedly. Below are examples on ResNet models trained on ImageNet, where uneven padding occurs 5 times, leaving out the right and bottom sides. The average filter in many layers is symmetric as we expect. However, around downsampling layers, the average filter is skewed at the top and left. If we increase the input size by just 1 pixel, which ensures that the input to each strided convolution has odd dimensions, we can get rid of uneven padding. And now, all filters are highly symmetric, as we want them to be. This visibly boosts the accuracy and the shift invariance on a variety of model architectures trained on ImageNet, as shown here. Note that the image size is increased by applying constant padding to 2 random edges of each input, which ensures that no additional image information is introduced when increasing the input size. I will now illustrate how 0 padding can induce line artifacts in the feature maps. Here you see example feature maps that a CNN backbone computes for 2 images. The first feature map in both cases contains an abnormal dark line close to the top that does not resemble any features from the 2 scenes. In fact, this line manifests regardless of the input. It is even visible in the mean feature map the filters compute for the test dataset. Different filters can induce different line artifacts in the feature maps they compute. Let's now investigate how these mysterious line artifacts emerge. Here we show the average feature map across all filters in each convolutional layer in the CNN. To simplify the maps, we use 60 random inputs instead of real scenes. It is evident that these lines originate at the border, where 0 padding is applied. Nevertheless, they can spread inward over successive layers and can hence disrupt the filter responses beyond the border. This can cause potential issues for downstream tasks. Here you see the same maps generated under mirror padding instead of 0 padding. Fortunately, the artifacts are reduced significantly, and the maps largely preserve the randomness of the input. This is because mirror padding fills the padding area by reflecting the border pixels, hence preserving the input statistics and avoiding salient edges of zeros. Let's now look at how these line artifacts can lead to issues in downstream tasks. This CNN backbone is trained to detect traffic lights. We tested the detectability of a traffic light stimulus at different locations by placing it over a blank image. As you can see, under 0 padding, the stimulus becomes undetectable when it lies within the area corresponding to line artifacts, where the activation for the feature detectors it needs are suppressed. Fortunately, these blind spots can be mitigated by using mirror padding throughout the CNN. The blind spots we identified with random inputs and an artificial stimulus apply to real scenes as well. Here we show a scene where the traffic light in the impact area is undetected. If we shift the scene upwards or downwards, the traffic light becomes detectable. By using mirror padding, which eliminates feature map artifacts that cause blind spots, we significantly improve the accuracy of the detector, as you see in the table.